Hello and welcome to section 14.4 where we are going to be talking about tangent planes and linear approximations, and then we're also going to throw in differentials at the end. So let's talk about the first thing, tangent planes. And so instead of finding the tangent line like we normally do for calculus 1, calculus 2 on a two-dimensional two-dimensional line in Calc 3, we're talking about a three-dimensional coordinate system. So what we're going to have is this curve, or this surface at the point wherever we want to take kind of the tangent. And so instead of having a tangent line of a curve on a two-dimensional surface, we're going to have now a tangent plane on a surface in 3 dimensions. And so this tangent plane means that at that point, so what's in blue is our surface, and that orange / type red part, that's going to be our tangent plane. And so what we want to do is we want to find the tangent plane at a given point on whatever surface that we have. And so in order to write the equation for a tangent plane, what we need is an initial point, and we need a normal vector to that point, or normal vector to this plane that we have. And so what we're going to do is we're going to denote the tangent plane to be this: ax minus x sub 0 plus b times y minus y sub 0 plus c times e minus c sub 0 equals 0, where a, b, and c is going to be parts of the normal vector, and x sub 0, y sub 0, z sub 0 is going to be the point in which we're taking our tangent plane, the point on the surface. So by dividing this equation, so what we're going to do is we're just going to rewrite this equation and divide everything by c. And if we do that and then shift everything over to the right, what we can say is, instead of writing our tangent plane equation that's highlighted, we can pretty much write this in terms of z minus z sub 0, where a and b are going to be negative ac and b is going to be negative bc, and so we can write our tangent plane in this form. So all we did was we just rewrote what's highlighted in yellow to give us a different form. Now, we want to know what a and what b are. So if equation 1, so everything that's going to be denoted, if it says equation 1, it's going to have that highlight right there. So that's equation 1. So if equation 1 represents the tangent plane at P, then its intersection with the plane y equals y sub 0 must be the tangent line T sub 1. Setting y equal to y sub 0 in equation 1 gives. So basically what this means is that, if we want to find, one of our tangent lines, so we want to find T sub 1, in order to find that, what we're going to do is we're going to find, kind of a vector that's going to be tangent at that point. And so we know 2 ways of finding vectors at that point, and that is taking a partial derivative. And so the first one's saying, okay, let's take the partial derivative, let's take it with respect to x. So if we're taking a partial derivative with respect to x, whatever y value we have that as our initial point, is just going to always stay y, that y value. We're not changing the y value. The thing that's changing is the x. So we're taking the partial derivative with respect to x. And so therefore, our a value is going to be the partial derivative of our function with respect to x at our point, x sub 0, y sub 0. And the reason why, the y goes away, because our y is always going to be that initial point, because we're going in the direction of x and that y is not changing. Similarly, if we make x equal x sub 0, so if we take the partial derivative with respect to y, then our b value is just going to be the partial derivative of our function with respect to y, where that we're going to have x sub 0, y sub 0 for our initial point. All right, and so putting that together, we can, write an equation. So this is, the equation that we're going to use to find the tangent. I don't know why I chose pink. The tangent vector, or sorry, not tangent, but tangent plane, is given by z minus z sub 0 is equal to the partial derivative of x at our initial point times x minus the initial x plus the partial derivative with respect to y at our initial point times y minus the initial y. And so that's all we got to do. So we're just taking partial derivatives to help us find, what our tangent plane is. And notice, it's very similar to finding the tangent line in Calc 1, Calc 2. Y minus y sub 0 is equal to the slope, x minus x sub 0. And so example 1, we want to find an equation of the tangent plane to the given surface at the specified point. So let's go ahead and take it. So the first thing that we'll need is here's, our surface is defined by z equals 3y squared minus 2x squared plus x. And we want to find a tangent plane at the point 2, -1, -3. And so what I'll need is I'll need the partial derivatives first. And so I'm going to take the partial derivative of x with respect to x and then with y. So let's do the first one with respect to x. So when I take the derivative, 3y squared just goes away. Minus 2x squared is going to be -4x plus 1. So there's our partial derivative with respect to x. Our partial derivative with respect to y is going to be 6y, and that's it. So nothing too difficult there. All right, now we're going to want to find the partial derivative of x at our point, and here we have 2, -1. And so we're just going to substitute in. So -4 times 2 is -8 plus 1 is -7. And then our partial derivative with respect to y at our point 2, -1 for the x and y. And so we're going to get, just plug that in, 6 times y. And so 6 times -1 is going to be -6. Now, using our above equation, we can go ahead and substitute in to find our tangent plane. So we're going to have z minus z sub 0, which is going to be -3, so it's going to be plus 3, is equal to our partial derivative of x at our initial point, x sub 0, y sub 0, which we found to be -7, times x minus x sub 0, which is 2, plus our partial derivative of y at our point, which we found to be -6. So I'm going to write minus 6 times y minus a -1, so y plus 1. And there's the equation. You can leave it this way, or we can go ahead and solve for z. So we could say or, and then we can just multiply. So z equals -7x minus 6y. All right, that's 6 a little bit better. Minus 6y. And then -7 times -2 is positive 14. Positive 14 minus 6 is 9. And then we have, not 9, that is 8. 8 minus 3 gives me 5. And there's the equation.